Hello everyone, my name is Mohammad Hassan and I am a PhD student here at Federal University of Ouro Preto. Today we are here to represent our paper titled as A Framework to Develop a Cost-Effective Charging Policy Framework. So now let's move to the presentation. So here is the title of our paper. We are here to represent a theoretical framework to reduce the total cost for the electric vehicle. And we are representing this to the 21st International Conference on Distributed Computing in Smart Systems and the Internet of Things. So here is the agenda for today's presentation. We start from the introduction, literature review, then the problem statement and motivation to write this theoretical framework, the tech framework that we proposed here in this research, some baseline methods for the comparison purposes, simulation setups, results, and finally the conclusion. So the environmental pollution is affecting the transportation system because of the fossil fuel generated by conventional vehicles. That is why electric vehicles, the EVs, are receiving considerable attention in the smart cities, and they are obviously the eco-friendly in providing the eco-friendly environment. EVs are a vital sustainable solution for the urban mobility within the Intelligent Transportation System (ITS). Research indicates so far that the optimal charging strategies can significantly mitigate the range anxiety, which is a formidable barrier to EV adoption. So that is why we are here to overcome this issue and provide reduced and more flexible total cost for the EV users. As the demand for EVs grows, it becomes crucial to optimize charging strategies to ensure cost efficiency for the user convenience as well as for the environmental sustainability. In the literature, we have found several existing solutions. For example, in paper 5, author produces a dynamic pricing model that incentivizes users to charge during non-peak hours. And of course, this will reduce the charging cost for the consumers. Without this, we have found authors also suggested vehicle-to-grid technology. By using this technology, the EV's user will return some electricity to the grid stations during peak demand periods, and of course it will help them to reduce their final total cost. Similarly, authors from 7 establishes a multi-objective optimization model for optimal charging and discharging strategies for the EVs, focusing on interest of distribution networks operators. So far we have seen some authors have discussed about partial charging, dynamic pricing, and V2G integration or some station placement methods. But the limitation that we have seen here is that authors ignore the real-time traffic or topography effect. So the problem statement and motivation for our paper is the range anxiety and charging inefficiency which hinder the EV adoption. We have considered these 4 points or parameters: traffic, which is denoted by D, energy consumption, which is denoted by E, charging prices, C, and topography effect, H. We have considered all these 4 points to create our tech framework. The need for optimization is current policies ignore dynamic factors like traffic congestion or uphill or downhill routes. And of course, if the vehicle is traveling to an uphill route, it will consume more electricity as compared to a simple or normal route. So the goal for this research is to minimize or reduce the total travel cost, which is indicated by TC in this research, through adaptive charging decision. Charging decisions are the rules which we have defined in this research and is denoted by CD. Especially, we have defined this theoretical framework to work on a large-scale network where a user needs to recharge its vehicle many times. And we have formulated an adjusted total cost denoted by ATC in this theoretical framework. Let us consider this is an instance for a network that we have considered in our research, where N0 denotes the starting point and N10 denotes the ending point. We have considered 9 different charging station positions starting from N1 to N9. So as you can see, on each station there are some values defined on each station, like traffic on the specific route, the energy which is required for a vehicle to go from one place to another, the topography effect which is on this specific route, and C is the charging price offered by each station. So the core idea of this framework is to minimize the total cost by adjusting CD charging decision at each station based on real-time parameters. The technicality is, as we have discussed in the previous slide, we have considered traffic, energy, charging and topography cost. At each station, the workflow for this framework is, at each station, it will compute the ATC, adjusted total cost, based on the mathematical equation that we have defined. Then it select the lowest ATC, which would be the best ATC to go on the next station. Then we apply some dynamic charging decision CD rules based on 0 to 20 scale to bypass or partially recharge. So here is the core idea of our theoretical framework. A vehicle should decide whether not to charge or charge at a specific value. The values for all of these 4 parameters are normalized in a scale between 0 to 20, like 1 to 20. So the purpose for normalizing this value is for easy computation. The cost parameters are charging cost, which is defined by Cj in the equations, and we have normalized as discussed on 1 to 20 scale. Traffic cost is the cost for the available traffic on the specific route and is denoted by Ti to j, traffic from specific location I to j. Energy cost is the required energy to be utilized by a vehicle to go from location I to location j. Similarly, topography effect is defined by Hj, and it is the uphill or downhill effect. Charging decision scales. We have defined these CD levels in our theoretical framework. For example, CD1 denotes to charge a vehicle up to +5 scale. CD2 defines to charge a vehicle up to 10 scale. Similarly, CD3 up to 15 and CD4 up to 20, and finally CD5 means not to charge at this station and the driver should bypass this charge and go on. The adaptive logic for this theoretical framework is it should increase the charging decision level if the traffic is greater than 10 or the topography effect is greater than 10. Then for the bypassing, the CD5 is to bypass the station if current charge is sufficient for the next level. So there are some key rules that we have defined in this framework. Rule 1 is always it should compare the energy required to go from station I to station J with current charge Cc old. It should be noted that Cc old defined in the paper is the current charge of the vehicle, and the vehicle should consider this charge and compare it with the energy required to go on to the next station. Rule 2. Bypass. CD5 should be taken if the current charge old is greater than or equal to the energy required to go to the next station and the topography effect or the traffic is less than 10. So the vehicle should bypass this charging station and not to charge. Rule 3 is set CD1 to CD4 as based on the energy required subtracted by the current energy of the vehicle that it should have. So it should decide whether the vehicle should charge up to +5 level, +10, +15 or +20. Rule 4 is boost the CD, means increment the charging decision by 1 level if the traffic or the topography effect is greater than 10. Rule 5 is always pick the route with the lowest ATC, which would be the best option for the user. So here are the dynamic programming setup of our paper. TC is denoted by total cost, and it is defined by equation 1. The total cost would be calculated by incrementing by the addition of energy required from station I to J, the traffic between I to J, and the charging cost offered by the station. We calculated the ATC, adjusted total cost, by equation 2, which is represented here, and where the ACJ is the adjusted charging cost from CD decision. Once the equation have defined the CD decision, then we calculate the AC, this adjusted charging cost, and we put this value in the equation 2 to get the ATC. Similarly, at each point we will define and we will find out the value of ATC. Once the value of ATC is lowest, so we should consider the lowest ATC to go on to the next station. It should be noted that at each station CC, the current charge new should be recalculated, because once the vehicle have recharged its vehicle, then on to the next station it must consume the energy and it should be subtracted from the previous charging value. So on each station CC new will be calculated in this format as defined in the equation 3. So we have defined some baseline solutions to compare with this tech framework. The number 1 is LDR, least distance routing. So in this solution, a vehicle should find the least distance station from its current position and go to that station and recharge there. According to LDR, as defined the values in table 2, the total cost have been computed as 167, and the route selected by LDR is N1, N2, N4, N6, N8, N9 and N10. These values are computed with the help of equation 1 as discussed in the paper. The second baseline solution is the LCR, which is least charging cost routing. In this case, each vehicle should consider the least charging cost offered by each station. So wherever it finds the least charging cost, it will go to that specific station and recharge its vehicle there. According to LCR, the total cost TC has been computed as 129, and the route which is selected by LCR is N1, 3, 5, 7 up to N10. So for the simulation steps, we have used Sumo simulation of urban mobility software, and we have run this for 1000 vehicles, and we consider the Tapas colony map of Cologne for this figure as it is shown in figure 2. We will show this on the next slide. So in the scenario as we have shown to you in figure 1, 9 stations have been considered from N1 to Nn, where starting point was N0 and the destination was N10. For the data sources, we have considered the real-time value via tracy command run by Python program on the Sumo simulator. Also, we considered the energy required from a vehicle which is utilized from one station to another. Each time we change the route on a specific route for a specific vehicle and consider these energy levels. The energy and traffic as shown here are the real-time values running on a Sumo platform, whereas we used the topography effect and the charging value which is offered by each station as randomly, because the H value, which is the topography effect, can varies from city to city. All of these values are shown in table 1, and we have already discussed this, that we randomized all these 4 parameters values in a scale between 1 to 20 for the easy computation. So here is the map for Tapas colony scenario, where the rectangle N0 shows the initial point for a vehicle and N10 represents the final destination. All of these charging stations were chosen randomly but for the energy required by electric vehicles and the traffic values was a real-time value by using Python script. The green line here represents the route selected by our framework tech. Here are the values which we have considered in this scenario. We found these traffic values on a real-time situation by using Python script in the Sumo simulation. Then we normalize these values between a scale of 1 to 20. Similarly, the value for energy required from going from station I to station J were considered this. Then we normalize this value up to scale between 1 to 20. The charging cost offered by each station were chosen randomly. Similarly, the topography effect values were chosen randomly. The TC values are considered as a naive approach, but we have defined ATC that a vehicle should consider this ATC for recharging its vehicle. So here are the results, the route selection and cost performed by LDR. This table represents the performance of LDR, which is, for example, on this specific instance, from going N1 to N10 is 167, where LCR is gone for 129 by following this route N1, 3, 5, N7 and N10. Here is the route performed by tech, and as you can see in the figure, this is the route N1, 2, 4, 6, 8, 9 and 10, and the total trip cost adjusted by tech framework was 114. So clearly this tech framework outperforms the both naive approaches from 12 to 32% in a manner of total cost. So here is a conclusion. We developed a theoretical framework for EV charging policies using simulation based data. We proposed here the tech policy integrates which consider 4 parameters: traffic, energy, charging and topography cost for the optimal efficiency for a user and EV driver. Tech minimizes total cost and maximizes efficiency in large scale networks. So the core area, the core goal for this research was it should be considered a large scale network where an EV driver needs to recharge its vehicle by several times. The dynamic programming DP equations also have been used, and some mathematical work have been done in this research. Finally, we consider the tech as compared to some baseline solutions, LDR least charging route and LDR least distance based route. For the future work, we will be defining this tech on some highway networks, and that's it from our side. Hope to see you guys next time in a person. Thank you so much.